students, and welcome to the lecture on function. After the lecture, we will be able to learn the following objectives. Discuss modular programming and functions. Understand function prototypes. Explain the type of functions. Let's start with a brief introduction to function. Functions are fundamental to writing modular code. They provide the basic mechanism for enclosing low-level source code, hiding algorithmic details, and presenting instead an interface that describes more intuitively what the code actually does. Functions present a higher level of abstraction and facilitate a divide-and-conquer strategy for program decomposition. A function definition contains the actual workings of the function, the declarations and statements of the function algorithm. The function is passed a number of input parameters and may return a value as specified by its interface definition. Function arguments are passed by a transaction termed passByValue. This means that the function receives a local copy of each input variable, not the variable itself. Thus, any changes made to the local variable will not affect the value of the variable in the calling function. Functions in C are recursive, which means that they can call themselves. Recursion tends to be less efficient than iterative code, but in some cases may facilitate more elegant, easier to read code. Here we will talk about modular programming and functions. Modular programming groups related sets of functions together into a module. The module is divided into an interface and an implementation. The module exports the interface. Clients' modules import the interface so that they can access the functions in the module. The implementation of the module is private and hidden from the view of clients. The division of programs into modules is a powerful organizing principle for designing non-trivial programs. Modules provide abstraction, encapsulation, and information hiding, making the large-scale structure of a program easier to understand. Modular programming. Programmers work with abstractions every day. An abstraction highlights the essential features of something while ignoring its details. An abstraction could encompass a piece of hardware, a software component, and so on. For example, a serial port can be abstracted to a pair of functions for reading and writing bytes to the port. The details of the UART, Universal Asynchronous Receiver Transmitter, its registers and addresses are suppressed. Implementations. Listing 1 is the implementation of an example module name. First, the module lists its dependencies on other modules. It imports the interfaces to the modules that it uses. This is done with the C preprocessor #include directive. The module uses the modules X and Y. The implementation of Z also includes its own interface definition. This allows the compiler to verify that the module's implementation matches its advertised interface. Listing 1, Implementation. Look at the screen to understand the implementations. Listing 2, Interface. Listing 2 shows the interface definition of our example module. Ignore the #defined at the top. We'll return to those shortly. The bulk of the interface declares the external, publicly accessible parts of the module. A client module can access the integer variable var1, or it can call function fun1 with an argument that is a pointer to an integer. Consider the simple C program shown on the screen. The program compiles without errors or warnings. The program has a simple mistake. Without the missing #include math.h, the C compiler assumed that the exp function expected an integer argument and returned an integer result. The addition of function prototypes to C made it possible to avoid mistakes like this. Function prototypes make it possible for the computer to check the types of arguments passed to functions, even when the function is defined in another file. However, C does not require declaring or using prototypes. Listing 3, Client.c, Implementation. Look at the example shown on the screen to understand listing 3. Look at the hash define in interface definition that we skipped earlier. The hash define for fun1 will cause any use of fun1 to be replaced with zfun1. Note that the hash define is strategically placed before the prototype for fun1. Consequently, the prototype is for a function named zfun1. Since the module interface gets included in the module's implementation source file, the actual function definition will be zfun1. When z.c is compiled, the function will be named zfun1 in the object file. If a client module fails to import the interface definition for z, its use of fun1 will compile to fun1. Need of user-defined function. C functions can be classified into 2 categories: library functions and user-defined functions. The difference between these 2 functions is library functions are already built in and we need not write its code, whereas a user function has to be written to get it executed during the output. However, the user-defined functions can become a part of the C library. In fact, this is one of the strengths of C language. Look at the syntax shown on the screen. Explanation of the syntax. Number 1, function header. The first line in the given syntax is known as header function. The function header consists of 3 parts: function type, function name, and the function parameter list. Function type. This may consist of the data types that we use. For example, float, int, double, whatever according to your needs. Function name. This may consist of any variable that is suitable for a user's understanding. For example, if you have made a user-defined function for factorial, then use fact, and if for simple multiplication, then mul. Parameter list. It declares the variables that are to be used in the function and that are going to be called in the program. Number 2, function body. The function body contains the declaration statement necessary for performing the required task. The body enclosed in braces contains 3 parts: a return statement that returns the value evaluated by the function. It's shown on the screen. Function statement that performs the task of the function. Use void as shown here. Local declaration that specifies the variable needed by the function. Look at the screen to understand it. Function calling. A function can be called simply using the function name followed by a list of actual parameters or arguments, if any enclosed in parentheses. Let's look at the example for multiplication of 2 numbers, which is shown on the screen.
Hi, and welcome to the first part of our discussion on modular programming. Systems are rarely designed by one person, and even if they are, it's good practice to make a product modular. A radio has several modules: the antenna, the tuner, the demodulator, the preamp, the amplifier, etc. A sustainable energy system has solar panels, a wind turbine, inverter, charge controller, battery banks. All of those are designed separately and independently, and then they're put together to form a complete system. Modular design allows us to break a big problem up into smaller, more manageable pieces. We can design, build, and test each module independently of the others. From this point on, all the programs you write will be modular, so it's important that you understand this material. So let's take a look at how software can be written in a modular fashion. Modular programs consist of several modules called functions. In other programming languages, they might be called subroutines or procedures. In C, we call them functions. So we'll take a look at a fairly simple program, one that converts Fahrenheit to Celsius, and see how the modules work together. I picked this application because it has modules of different types, functions of different types, and it pretty much shows us all the different ways to use functions, at least the main ones. So if we take a look at this, we have a main program here called the Fahrenheit to Celsius program, and we have three functions built into this main program. We have a function called getInput, a function called convert, and a function called displayResult. Here's what the program looks like when you write it in C. Okay, it's going to look a little Greek right now, and of course in C it would be one continuous, straight down the page type of program. I picked this application also because it's kind of small, and I apologize for the small print, but I wanted to get everything on one screen so that you could see all the whole thing operating at once. So over on the left hand side you see the main module, and over here we see the three individual modules that main calls or uses to get the job done. So over here is the main function. Okay, you've all seen void main with an empty set of parentheses, so that's our main function. And in the main function calls three other functions to do the actual work. You can think of the main function as kind of like a manager who delegates responsibility. The manager oversees the whole thing, and these are the ones that actually do the grunt work. They get down and dirty and do the actual stuff. So these are the functions that the main function calls. So we have a function called getInput, a function called convert, a function called display. So let's look at the big picture of the main function. We'll ignore the guts of the other functions for now. So let's take a look here. We've got, well, you already know about variable declarations inside of main. Okay, so here we have a function that says get the input and assign it to a variable called Fahrenheit. Here's a function that says convert the Fahrenheit value into Celsius. So take Fahrenheit, convert it, and assign the result to Celsius. And here's something that says display the result in Celsius. Okay, notice that with some good names here, I don't even have to put any comments. It's self-documenting code. Okay, so when you look at it as a big picture, it doesn't look all that complicated. This is why we break up programs into functions. It makes big programs manageable. So once we write the main function, we can look at the details of how the other functions will work. So we'll trace through the program to begin with as it executes, and I'll describe the parts, ignore other parts, okay? Eventually we'll discuss everything, but we'll just do it a little piece at a time. So in here we have a couple of variables that are declared inside of main, so they're only known inside of main, and these are called Fahrenheit and Celsius. Float means that they're floating point numbers. That means they can deal with a decimal point. Okay, here's an assignment statement when we call the getInput function. So we have the function name, and its result will be assigned to the variable called Fahrenheit. Remember that an assignment statement has usually a variable or a port on the left and some kind of an expression or a value on the right. In this case, it's an expression. It's even a function call. Okay, this is the getInput function that actually does it. So when it encounters this statement, when the main function is executing and it encounters this statement, the first thing it does, this is a call to the getInput function. So the first thing that happens is main goes up to the getInput function and starts executing here. GetInput has a local variable called input, okay, also a floating point number. Don't worry too much about the printf and scanf. We won't be using these in our programs, but these are built-in C functions that print something on the screen and read from a keyboard.
Let's now learn about function prototypes. A function prototype is a function declaration that specifies the data types of its arguments in the parameter list. The compiler uses the information in a function prototype to ensure that the corresponding function definition and all corresponding function declarations and calls within the scope of the prototype contain the correct number of arguments or parameters, and that each argument or parameter is of the correct data type. Old style. Functions can be declared implicitly by their appearance in a call. Arguments to functions undergo the default conversions before the call. The number and type of arguments are not checked. Prototype style. Functions are declared explicitly with a prototype before they are called. Multiple declarations must be compatible. Parameter types must agree exactly. Arguments to functions are converted to the declared types of the parameters. The number and type of arguments are checked against the prototype and must agree with or be convertible to the declared types. Empty parameter lists are designated using the void keyword. Ellipses are used in the parameter list of a prototype to indicate that a variable number of parameters are expected.
Going over functions quite a bit the last few lessons, and you may have been messing around with the functions those two that we had above main, and you may have moved them below main or something, and if you did that and then you build and run, you get errors. And you may be saying, why am I getting these errors? I have all the code right, I just moved them. Well, yes, you had all the code right, but you didn't in a way because you didn't use a function prototype. And what are they? Well, they inform the compiler that it will eventually see the function, because you're delegating part of the responsibility of main off to this other function. So it needs to know that there's going to be a function there to run what main is depending on it to run. So if this is the function, void spend dollar, double dollars, and then everything inside the braces, the function prototype is void spend dollars, parentheses, double dollars. And you put the function prototype where the function was, and then you can move that function any place in the program and it'll be fine. You can move it below main and there won't be any errors because main already knows that there will be a function there to do what you said spend dollars would do. So it's a real simple concept, but one that you do need to know. Otherwise, you can get in a lot of trouble and you really don't know why. Well, now we'll be going into Xcode and go over this a little bit in code. Okay, here in Xcode, we're going to be trying out the function prototypes, and this is the function prototype right here out of this function, so you can just copy and paste that right here. And I didn't tell you this in the keynote, but make sure you do end it with a semicolon. Otherwise, you'll get lots of errors. And then you can just drag this function down below main, and really function prototypes just give you the freedom to put your functions anywhere in your program that you would like to, anywhere that you'd like to put them. Copy and then paste it. Remember, end it with a semicolon, and you can drag it down below. So now you have your main function right here, and then you have your extra functions that you delegate certain responsibilities to in your program. Build and run, save all. And as you can see, it build and ran correctly, nothing wrong. So I know this was a real quick lesson, but I just wanted you to really understand the importance of function prototypes and what they can really benefit you in your program, and they give you a little bit more freedom too.
Prototype syntax. A prototype is identical to the header of its corresponding function definition, specified in the prototype style, with the addition of a terminating semicolon or comma as appropriate. Function prototypes need not use the same parameter identifiers as in the corresponding function definition, because identifiers in a prototype have scope only within the identifier list. Moreover, the identifiers themselves need not be specified in the prototype declaration. Only the types are required. Scope and conversions. Prototypes must be placed appropriately in each compilation unit of a program. The position of the prototype determines its scope. A function prototype, like any function declaration, is considered within the scope of a corresponding function call only if the prototype is specified within the same block as the function call, any enclosing block, or at the outermost level of the source file. The compiler checks all function definitions, declarations, and calls from the position of the prototype to the end of its scope. The syntax of the function prototype is designed so that we can extract the function header of each function definition, add a semicolon, place the prototypes in a header, and include that header at the top of each compilation unit in a program. Function prototypes are declared to be external, extending the scope of the prototype throughout the entire compilation unit. Formal and actual arguments. Calling programs pass information to called functions and actual arguments. The called functions access the information using corresponding formal arguments. When a function is called, the tasks performed are: all actual arguments are evaluated. There is no implied order in which these arguments are evaluated, but all arguments are evaluated and all side effects completed prior to entry to the function. Each formal argument is initialized with its corresponding actual argument in the expression list. Conversions are done as if by initialization. Both standard and user-defined conversions are performed in converting an actual argument to the correct type. The initialization performed is illustrated conceptually by the code shown here. Now we will discuss the types of functions. All functions have a type. They return a value of that type whenever they're used. The reason that C does not have procedures, which in most other languages are simply functions without a value, is that C, it is permissible, in fact it's mandatory, to discard the eventual value of most expressions. Functions can return any type supported by C, including the pointers, structures, and unions. For the types that cannot be returned from functions, the restrictions can often be sidestepped by using pointers instead. All functions can be called recursively. Declaring functions. Unfortunately, we're going to have to use some jargon now. This is one of the times that the use of an appropriate technical term really does reduce the amount of repetitive descriptive text that would be needed. With a bit of luck, the result is a shorter, more accurate, and less confusing explanation. So here are the terms. Declaration. The point at which a name has a type associated with it. Definition. Also a declaration, but at this point some storage is reserved for the named object. The rules for what makes a declaration into a definition can be complicated, but are easy for functions. We turn a function declaration into a definition by providing a body for the function in the form of a compound statement. Formal parameters. These are the values used as arguments when the function is actually called. In other words, the values that the formal parameters will have on entry to the function. The terms parameter and argument do tend to get used as if they were interchangeable, so do not read too much into it if we see one or the other in the text. For example, you might be intending to use a function in a private library called, say, AAX1. Now look at the screen to see how it should be used. The return statement. The return statement is very important. Every function except those returning void should have at least one, each return showing what value is supposed to be returned at that point. Although it's possible to return from a function by following through the last, unless the function returns void, an unknown value will be returned, resulting in undefined behavior. Look at the example as shown on the screen to understand it. Arguments to functions. Before the standard, it was not possible to give any information about a function's arguments, except in the definition of the function itself. The information was only used in the body of the function and was forgotten at the end. In those bad old days, it was quite possible to define a function that had 3 double arguments and only to pass it one int when it was called. The program would compile normally, but simply not work properly. It was considered to be the programmer's job to check that the number and type of arguments to a function matched correctly. Look at the example and use of function with arguments as shown on the screen. Function definitions. Function prototypes allow the same text to be used for both the declaration and definition of a function. In either a definition or a declaration of a function, It serves as a prototype if the parameter types are specified. The old C syntax for the declaration of a function's formal arguments is still supported by the standard, although it should not be used by new programs. Look at the function shown on the screen. Because no type information is provided for the parameters at the point where they are named, this form of definition does not act as a prototype. It declares only the return type of the function. Nothing is remembered by the compiler about the types of the arguments at the end of the definition. Now in the end, let us summarize what we have learned in this lecture. A function definition contains the actual workings of the function, the declarations and statements of the function algorithm. Functions in C are recursive, which means that they can call themselves. Recursion tends to be less efficient than iterative code, i.e., code that uses loop constructs, but in some cases may facilitate more elegant, easier to read code. The module is divided into an interface and implementation. The module exports the interface. Clients' modules import the interface so that they can access the functions in the module. The interface definition has a list of functions and data structures to export, as well as the declarations of these functions and data. These are the only parts of a module that clients can use. Library functions are already built in, and we need not to write its code, whereas a user-defined function has to be written to get it executed during the output.